Hello. Hopefully I can master this remote quickly. Oh, you just use the keyboard. Okay. Adaptive control here. Okay. Well, let's see. Okay, my slides are, there they are. Yeah, I got them. Let's see. Okay. Okay, hello. Again, I'm Terril Hurst from Raytheon. I would first of all like to acknowledge a few people. Dr. Jefferson Taft is a data scientist now at Microsoft who was really key in a lot of the framework that we're going to be discussing today. My coworker, Dr. Kevin Rotz, is here to answer the hard questions, so he's close to the mic, sir, so he can answer the hard questions. We're going to be talking about a decision-theoretic framework, and it's decision-theoretic in two senses. One is to decide where to sample with a simulation experiment based on information as we collect as we go. But the other thing is we're talking about how to most effectively quantify uncertainty so that when you're through with your simulation experiment, you have an idea, you have a risk-informed kind of capability for making your decision. And I would like you to pay attention to this heat map that Kevin put together. This is a 2D subspace projection of what's called mutual information. That's a key concept in this adaptive simulation framework. And if this is a new concept to you, I really enjoy the Wikipedia page on mutual information. It's a really good starting point. And if you don't remember anything else from this talk, I strongly encourage you to go look at that mutual information page because it'll start sinking in because we got to move pretty quickly through this. So, you know, I've been involved. I did my PhD in the mid-'80s, and even since then, the rise of modeling simulation analysis. And by the way, MSA, we have to repurpose our TLAs here, right, our three-letter acronyms. It does not mean measurement systems analysis conducted to like with gauge reproducibility, repeatability. I know we're in a test place, and that's probably what MSA means to you, but to us, modeling, simulation, and analysis, that A is critical. That's why we put it right in there with the M&S, no ampersand, modeling, simulation, analysis, MSA. But in some ways, I view it unfortunate that building and running simulations has become so easy. It's actually too easy. Just like writing software, in my opinion, is too easy. Writing good software ain't so easy. Same thing as John was talking about. Validating, getting a credible simulation is not easy. And so it's much harder. So it really does require fully quantifying the uncertainty. I encourage you to study that's called the VVUQ literature on that, the verification validation for uncertainty quantification. ASME is a real satellite, Sandia Labs, for example. So a sponsor of our work here, the sponsor were the IT folks and the Digital Transformation Initiative at Raytheon. And we get asked to provision high-performance computing systems for engineers who just want to run and run and run data and just crazily do Monte Carlo studies and pretend like they have this tight confidence intervals and they really believe stuff, right? Because they got this tight confidence interval. This is where statisticians could kind of come and help. You sure that's getting you any information? But we're trying, there are innovations that have happened, and already was mentioned Latin hypercube sampling. That's very key to the way we do simulation experiments, as well as surrogate models. If you've read the Santner book, Design and Analysis of Computer Experiments, that's a great reference for Gaussian process models to do random functions of, say, it could be a deterministic simulation, but those Gaussian process models are incredibly powerful tools. But these innovations introduce new issues and options and trade-offs. You know, we could do, because of the speed up of computers and high-performance computing, you can do a fixed number of simulation runs could be done in a much shorter time today than 20 years ago. Or conversely, one might imagine, well, let's do more sim runs, and maybe we get more precision out of this. And you say, oh yeah, let's just drive that confidence interval down smaller. And so what we assert here is that the framework we're going to talk about for adaptive sampling is more efficient for quantifying uncertainty than what I will term generically in a priori sampling. That is, deciding ahead of time where to do a fairly large simulation experiment, number of treatments. We're going to talk about comparing a priori sampling with adaptive sampling, and 3 examples we're going to give. So we're introducing a thing we call the ASHI loop. ASHI is an acronym. It stands for Adaptive Sampling for High Performance Computing Improvement. And we'll go into the details of this framework in a couple of slides, but it begins and ends with, sorry, I got to be careful here what I touch, with a query variable. Okay, we treat that as a random variable, a very mathematically precise question to be answered, and it ends with, if we've decided we have enough precision in that query variable, we stop. We prime the ASHI pump with a relatively modest size Latin hypercube sample, but then we start conducting inferences using a set of models that I'll talk about on a later slide until we are able to say we're satisfied that our model is now sufficiently unwrong. I love Box's quote. That's how I get my daily endorphins, is to quote my favorite statistician, all models are wrong, some are useful. Everybody's nodding their head, amen, they're saying amen, so I think I'm in good company here. So again, the query variable plays a central role in ASHI. We regard it as a random variable. So what we're doing is we're calculating a probability, think of it as posterior probability of the value of the query variable given the data that we're observing from the sim runs until that time. And then that query, that distribution should fully reflect uncertainty that's arising from sim modeling assumptions, which we're not covering in this paper. That's an area we're working on, and as John was talking about. The uncertainty due to the finite sim run data, and then the uncertainty in the surrogate model parameters, which are generically called theta. And so ASHI checks, as I said, whether that sufficient precision in the query is obtained before deciding to submit additional runs to the grid. And so again, begins and ends with the query variable. Now these 4 interconnected models, I'll just introduce them here, and we'll show examples of them in the remaining talk. The surrogate model, that's, for example, a continuous correlated beta process. If you have a binary outcome, you hit or you miss a target. A continuous correlated beta process is a fantastic type of surrogate model to have that theta that become, and I'll talk about that surrogate model parameter theta in a moment. An information model, and this is where mutual information that I mentioned on the title slide comes to play. And so that surrogate model and the mutual information model go together, again, with a cost model. That is to say, well, we're trying to predict how much runtime is this going to cost. We may very well have multiple fidelity options, and we're trying to do a mix of high and low fidelity options. So we have to have a cost model to say, what's the cost for getting that information out of our simulation runs. And then the grid model is really representing the state of our grid resource, and then that we help schedule the runs. So ASHI uses Bayesian inference in order to formulate and update these models as sim results arrive. So just a couple more details. Apologies if this gets a little bit mathematical. I mean, I'm not trying to be like Dr. Veckman and say it's technical on Ghostbusters. I mean, I love Ghostbusters. It's technical, but this is a little technical here. The mutual information that was pioneered by Shannon, really, in entropy. It was not called, if you read the research, Shannon did not call it entropy. That was a later thing. But this is the mathematical expression for mutual information. We have this joint probability here times the log of that joint probability of our query variable, random variable, and our sim output, divided by the product of the marginal probabilities of those two. That's what defines mutual information. Now notice that log, if let's say the numerator and the denominator were equal as in independent query variable and and sim output were equal, that log would be 0. We would get no mutual information. What we do is we make them conditionally independent given a vector of parameters theta in the surrogate model. And so we can imagine if we were just happy with doing point estimates here, well, guess how much mutual information we would get out? 0. So we have to have a full probability distribution in order to make this ASCII loop go. And so we're going to, there are different surrogate models that have thetas embedded in them, Bayesian linear and generalized linear regression models, continuous correlated beta process I already talked about, Gaussian process regression. These are all candidates, and we're going to see some examples in the remaining time we have of all of these. So the first case we have is one that IDA, I think, cares a lot about. I've met with folks here at IDA, and is our missile complying with the performance requirement? We can't fly enough flight tests to do that, so we have to trust our simulation and get somehow prediction performance out of that. So it's a compliance with the system performance requirement. The second one we're going to talk about is a response of our sensitivity to the control factors in our experiment. The third example is engineering design optimization of a guidance algorithm, and we want to set gains and times to go for switching gains. So turning to the first example, the query, as I emphasized many times, you start with the query. We want to quantify the probability that we're going to comply with this requirement. The probability of system success shall be at or above 0.85 over at least 60% of the target's engagement of the system's engagement space, which is defined in this case by those factors that you see there. And we have a table on each example. This table, the upper part of the table, gives the a priori sampling that we did. In this case, we did 1,000 treatments in that engagement space, each replicated with Monte Carlo draws 32 times. And our surrogate model is simple, and for a priori sampling, just a summary statistic. And we'll talk about on a later slide the CCBP for ASCII. But now you see this CDF, empirical CDF here. Because we did 32 Monte Carlo replicates, we have a 33 steps, and they're 0 for 32 up to 32 for 32. On our estimates, our point estimates of the probability of success for each of those engagements that we're claiming because we did Latin hypercube coverage, that represents our engagement space. Now, notice the green line here, the box. We're basically saying that no more than 40% can have an estimate of probability of success less than 0.85. Unfortunately, if you look at the magenta line, well, guess what? For this data, it shows, oh, shoot, 51.5% have that. Well, unfortunately, even if we appeal to a confidence interval, it's not spanning 0.85. So sorry, confidence interval is not going to bail us out here. So it's really clear that we have a performance gap here at the cost of 32,000 runs. Now, there's an intermediate step between that method and full-on ASCII, and we call that ASCII light for probability of non-compliance. Now here, what we're doing is this 1 minus the probability that we're meeting that requirement at a local engagement. And so we still have a priori treatments that are selected, but we vary the number of Monte Carlos. And so we don't do fewer than 8 or more than 100. And so we'll use a conjugate prior, and that we have now an analytic solution. And so we can stop beating thoroughbreds or stop beating dead horses when the probability of noncompliance either goes below 0.05 or above 0.95. There's no point in sampling more. Now, unfortunately, there are always some too close to call ones. So we get to our limit. We're on that compliance boundary. In this case, there were 155 unresolved cases that are just still too close to call. We could have used some of our runs saved on these other ones there, but that's one thing we could have done. So that's called ASCII light. It's a smarter way to use your sim runs. ASCII full on is using this CCBP. Now, I apologize. This equation looks scarier than it really should be. All it is you have a beta distribution here, and you are summing up with a Kronecker delta function the successes and the failures. You're weighting them by a kernel smoothing function, which has to be vetted. We have to feel comfortable with that smoothing function. But then this is how we do a spatially correlated model. And so what we're doing at any point in that space is we're doing a single Bernoulli trial, and then we're borrowing information from the outcomes in the neighborhood to estimate what the probability distribution of probabilities is looking like. And so using that model on this left plot, on the left, we see that by 3,000 runs here, that model is predicting kind of, you're starting to see an emerging passing region in the space. On the right is the failing, and then that salmon colored is like too close to call. Now, notice here what sampling, guided by that CCBP and mutual information, notice how ununiform this sampling is. It's sampling at the boundary. It's like, I need more information. That's where the highest mutual information is. Go sample at that boundary. So you see how this adapts. Now, we ran this up and beyond 15,000 sim runs, which is still half of the 32,000. But even by then, it's pretty clear where you're passing region and you're not passing region. The too close to call region has collapsed. But even as far as meeting that requirement, this is just a history of the sim runs. Notice that green area on the top, it's growing, it's asymptotically shrinking its growth rate, but as soon as it crosses 40%, we can call it. We can call this election. We say, no, you didn't make it. A Democrat won. Sorry, I just didn't mean to get political there. But so look at the 32,000 versus 6,000 runs, and Ashy Light was in the middle there. So what we maintain is that by this adaptive sampling, we have at a reduced cost quantified more carefully, more fully the uncertainty with a Bayesian posterior probability model. The second example is inspired by one of law simulation modeling and analysis. If you guys have that textbook, there's a small factory modeling example in that textbook where you have parts arrive, they're placed into a FIFO queue, and there's a machining operation. The inspection is then done, taking things from a queue, and then some fraction are bad, they have to go be reworked, and then those that are good are gone, leave the system. So with this, we had 200 treatments with 32 Monte Carlo replicates per treatment, and we built an ordinary least squares third-order polynomial model. And so in the process of doing that, what the query was, we want to know where is the sensitivity, what's the max sensitivity, where is each factor of those times, the machining time, the inspection time, and time between going down, where are we most sensitive to those? And so we fit a third-order max likelihood least squares model to the 6,400 runs, and we get these nice, beautiful, clean-looking, crisp contour lines here. And you can see that in the upper left, you see how the gradient is really saying, get that inspection time down. That's the y-axis. Apologies, it's so small, probably on your screen here. And over in the lower right, we say, well, get that machining time down. And in the middle of those upper left, upper right, you can see that gradient is kind of morphing, okay? So we have a plot that Kevin developed. I think is one of the coolest plots he's ever done, other than the fire plot on the cover here that I showed you. It's called a max sensitivity plot. And so what you do, if you could limit to three factors, you color code the region using the surrogate model where it's telling you want to improve throughput, get this factor down. So you see the upper left again is inspection time down. The lower right is machining time down. And then there's this little interesting blue island here where you're machining things so fast, inspecting things so fast, that what dominates the story is the time the machine can stay up. So it's pretty cool. And so, you know, non-Bayesians feel really cool. This is okay. Now let's see what happens when you go Bayesian on this. Okay, so here's looks like my granddaughter was a crayon on the contour plots, right? Actually, she did do this. No, I'm kidding. Kevin did this, but She could have done it probably, but that's what a contour plot looks like with the posterior probability distribution of throughput. And what is cool with the max sensitivity, when you have full probability model going for you here, you get this mixing of sensitivity regions. So you get, it's not just those crisp boundaries of where are you most sensitive to what. It's probabilistically being reported. And here is the equivalent mutual information plot, similar to the one on the title page, where the dark regions are saying you don't need a sample anymore here. You're getting little or no mutual information there. But the hot regions, those yellow, those bright yellow, you need to sample more here to determine where is the sensitivity the highest. So that's the Bayesian alternative to sensitivity analysis that was enabled by our adaptive sampling. The third and final example is we used, again, a 6-degree freedom simulation. And the query was, well, we have 4 design variables for a guidance, Gen X, generalized explicit vector guidance. And these 4 design variables, we want to optimize performance by setting those at the quote, optimal value. And so here we had 200 treatments with 6,400 replicates. And we tried, this particular problem did not lend itself to a usable for optimization surrogate model. We had a second criterion that says at the optimum suggested, we want that credible interval to be no wider than 10% around the probability of success. And we, with max likelihood sampling, a priori sampling, we could not achieve that 10% credible interval. This is a Bayesian analysis done on that a priori data. That's what's plotted in the lower right plot here. So we did not meet it. However, with adaptive sampling, we were able to meet that, not with 12,800 runs, a priori runs, which we did not meet it with, but we met it with 5,850 runs. And just to pile on here, we were able to achieve the same credible interval that a priori sampling did in only 2,350 runs. So in both cases, significantly fewer runs, but because we had a posterior probability distribution going for us. So, in summary, we believe that for credible modeling simulation analysis, the experiment's query has to be precisely posed, mathematically posed, and the uncertainty quantified. And surrogate models, you can see, hopefully, that have played a key role in this, in quantifying that uncertainty in the query results. And we believe that ASHI efficiently answers the query using both surrogate models and mutual information, choosing where the sample given SIMRUN results. And so this is a summary of the results. It was 81% savings in SIMRUNs for the compliance requirement. We had higher certainty in the system's max sensitivity regions. It was not so much a question there of efficiency as much as more fully quantified uncertainty. And in the third example, we saved more than 50% of the runs to achieve a desired credible interval, and greater than 80% runs were saved to get to the same credible interval that a priori DOE sampling would have given us. So we think this is a major step forward. We're integrating this into our HPC operations. We're formalizing more and more queries, but also teaching people is a crucial area that you have to be careful about the query to start with, and that's where the story ends. So thank you.
If you have any questions, please put them in the chat and I will ask them. I do have one question. This is really impressive. Are there any edge cases or scenarios that ASHI struggles to produce these wonderful results? Like what are some confounding issues that it might not be able to work as well on?
Yeah, that's a great question. I think edge cases, I think we presented, for example, the surrogate models that worked. Now, Kevin occasionally ran into, this isn't working out so well. I mean, if you get a covariance matrix that's a 10,000 by 10,000 covariance matrix, that probably means you should shift surrogate models, right? I mean, lack of data is not an issue in sim. Lack of credible data maybe. That's the validation calibration. But so edge cases, that's the best way I could say it. You have to have enough knowledge. You have to have enough quivers in your Bayesian arrows in your Bayesian quiver to handle those kinds of cases. And I guess another thing would be in the ASHI loop, there is some overhead for computing things, to decide where to sample. If your sim is running really quickly and it's sitting there waiting for you to compute, it's like, why are you doing this? So it becomes a trade. Slower running sims, you can justify more sophisticated surrogate models and sampling. But thank you.